Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends. We will now discuss some important design aspects of tubular members under the SwayamPrabha course titled Maritime Structures offered at IIT Gandhinagar. Friends, welcome to lecture 33 where we are going to discuss about the codal provisions for designing tubular members, essentially cylindrical members. Now you know cylindrical members or tubular members are most common cross sections used in offshore structures, being it steel as the most preferred material. So we will discuss the design aspects when these members are subjected to different kinds of loading. So what are the possible loading a member can experience? A member can experience the possible loads as one, axial load. When I say axial load, there can be axial tension and axial compression. So friends, it is very interesting for us to realize that the design aspects of members under axial compression is different from that of tension, because in compression buckling comes into play, whereas in tension such issues do not arise. The second one could be bending. The third one could be shear, and the fourth one could be hydrostatic pressure, and the fifth one could be buckling stress or hoop buckling stress. Now, the design issues related to these kind of behavior under different loading are to be looked into detail if I am to understand the design of members under this kind of loading. Incidentally and unfortunately, these loads can also be combined. So, under the combined action of these loads, then the design check procedure is different. Citing one of the international codes for design, where we say American Petroleum Institute recommended practice for design. Now, we are using APRP 2A, which is essentially used for working stress design. Now, let us talk about the design methods. There are two kinds of design methods which are popular in the literature. One is what we know popularly call as allowable stress method. The other one is limit state design. In allowable stress method, the load is estimated based on the historical data for a specific weather window and sea state. The load effects caused by these loads are estimated based on the structural mechanics principles, and then we apply suitable factor of safety to the overall strength of the member. So, this procedure in nutshell is embedded in allowable stress method design, whereas alternatively the limit state design method uses probabilistic approach. The moment I say probabilistic approach, they will start characterizing the loads as well as the strength by some factors. This is not a new procedure. Even in limit state design method applicable to concrete structures of design as practiced in IS 456, and also limit state design method as practiced for steel IS 800 Indian Standard Codes of Practice. We have already learnt about these probabilistic tools where we say characteristic strength of material and characteristic strength of loads. What we understand, their factors are gamma m and gamma f, where this is characteristic strength factor of material, whereas this refers to characteristic strength factor for loads. So, anyway, this follows also a probabilistic approach of design. So, it is not new that which has not been done. So, limit state design follows probabilistic approach. It uses characteristic variation of loads and materials. So, we call here the difference material strength as resistance. Okay, that is the difference we announce here in this codes of practice. Loads will stand as loads, whereas strength of material is referred as resistance offered with the structure. So, as usual, we have load factors and resistance factors, that is gamma f and gamma m, which are applied to the material or the resistance and the loads on the structure to obtain the characteristic variation of these values, and then they are applied onto the structure to check or to prepare the design procedure. So, allowable stress method and limit state method are two broad design methods which are practiced in maritime structures, especially in steel structures. Let us look both of them slightly in detail before we take equations governing these design factors. Let us talk about allowable stress method design. Now, whenever you talk about a design procedure, there are two quantities which are to be compared. One is what we call demand, other is the capacity. So, design is safe, a design is said to be safe when the capacity exceeds the demand, right. When the capacity of the material or the structure exceeds the demand imposed on the structure, we call this design procedure as safe. Worst by worst, it can be equal, but of course, the capacity cannot be lesser than the demand, it is causing failure to the structure. So, two parameters of the paramount importance in design are capacity and demand. Let us see what is the demand in this method. The demand comes from the loads actually. The applied stresses caused by these loads on materials or members are calculated based on the principle of structural mechanics. So, we do a complete analysis of the structural system, subject these loads onto the system. The loads can be wave loads, can be wind loads. We discussed them in detail in the previous lectures. So, at any given point of time in space, depth and time, we know what is the wave load imposed, and from the wave water particle kinematics we can compute the wave loads. Similarly, from 1/7 power law we can compute the wind loads. Once I know the wave load and wind load, so I can calculate the stresses on the members and the support conditions based upon principle of structural mechanics. So, we will use the principle of axial, bending and shear or combination of all to find out the demands. So, we can compute easily the applied stress, and we all now agree that applied stress will be a function of geometry, section, shape and size, and of course, the thickness of the section and the stiffness offered by that section. So, if it is axial, it is AE by L, if it is bending, it is EI by L, we know that. Okay. If it is axial, we use axial rigidity, if it is AE by L. If it is bending or flexure, we use EI by L, which is called flexural rigidity. So, this is the axial stiffness and this is the bending stiffness. Okay. So, I will use the respective stiffness values based upon the type, and of course, I will talk about the shape and size and thickness and the geometry or assembly of members to compute the demand on the structural system globally and also locally in each member. Okay. Demand can be computed. Now, let us talk about the capacity, where the capacity is coming from. Obviously, we all know the capacity has to come from two sources, one from the material, two from the degree of indeterminacy the structure is offered to. Okay. So, the allowable stresses are obtained as a fraction of the material strength in this design. The material strength, we always recognize this as yield strength, we call this as Fy, APRP uses capital Fy. Okay. The yield strength of the material, we do not use the full yield strength, we take a fraction of that yield strength as the allowable stress. So, allowable stress in sense actually is a yield strength divided by factor of safety. Okay. The factor of safety can be 1.2, 1.5, 1.15 and so on, depending upon the combination of forces. We will see them later. So, depending upon the material strength factor of safety applicable, we compute the allowable stresses. Once the allowable stress is known and applied stress is known, it means the allowable stress will lead to capacity and applicable applied stress will lead to demand. We use this equation and say the safe design is capacity should exceed the demand. Okay. It is a basic principle of design, we all know that. So, in allowable stress method, the important parameter which we must understand are two things. One, yield strength is divided by factor of safety to get capacity of the material. So, we do not use the full strength of the material in design. Okay. We divide it by a number. Factor of safety is definitely more than 1. Okay. So, we divide it by a number. The second point, the demand estimate is based on the stiffness of the member, the geometric configuration of the member and the section and its thickness of the member. So, I can now say demand is more or less geometric driven or geometric dominant property, capacity is more or less material driven property. Okay. So, for a good design we say capacity should exceed the demand, right. Capacity should exceed the demand, or worst by worst it can be equal to the demand. So, that is allowable stress method in general. So, loads are estimated in this method based on historical data. So, what you do? You look into the wave load, wind load history for the past 50 years, 100 years, etc. So, when we choose about this, we will come across something called return period, which we discussed in the previous lectures. So, return period will help me to find out how long I have to observe the record to compute the historical data from which I will estimate the loads. Okay. So, amongst this historical data collected, this method advocates you to pick up the maximum load. Okay. That is important. Whether the maximum load will get repeated within the service life of the structure, this question is not attempted at this moment. From the historical data, pick up the maximum load, consider that as the demand. Okay. However, loads also vary probabilistically, but in this method the probabilistic exceedance of the load is not considered. So, allowable stress method is a deterministic approach of design, it is not probabilistic based method at all. Therefore, the probability of exceedance of any chosen design value within the service life of the structure is not a part of the game in this design process. That is about the loads. Now, once the loads are applied to the structure, I will do detailed analysis to compute the stresses. It can be bending stress, it can be shear, it can be axial, it can be torsional, etc. Right. To compute the stresses, I need to know the structural system and the cross sectional dimensions and the structural or the member thickness. I find the response of this using elastic theory. So, this method of design is purely elastic because it does not promote any permanent deformation on the member as well as in the structural system. Okay. So, based on the linear elastic theory, you can compute the responses. While doing so, assume the worst possible combination of loads. Loads are of different types, different nature, different intensity, different direction of application, different space variation and time and depth. We have already seen them in the previous lectures. So, take the worst combination, okay. Pick up the worst combination of these forces, apply them on the analysis, do elastic analysis, get the responses, that is your capacity. So, the demand and the capacity or estimate. Now, let us take for example, what combination do you consider? If you have dead load and live load, you actually add them. If you have dead load, live load and environmental load which comes from waves, wind, etc., simply add them. If you have dead load, seismic load, add them. These are examples. However, the factors of multiplication of these, okay, vary depending upon the advice offered by different international codes of practice. Okay, we will see them in detail when we touch upon the design example. Okay. So, I can now look at the worst combination of loads, do elastic analysis, find the response, that gives me the capacity. Look at the historic data, take the maximum value, that gives me the demand. Now, for a good design, I must have capacity exceeding the demand or worst by worst equal to the demand. Okay. So, this becomes my rule or the analogy for following this method. So, this method is called allowable stress method, okay, allowable, permissible, etc. Let us see what is the design procedure for this. The design loads are defined as the maximum loads that occur during the lifetime. How do you get this? You look at the historical data available from the site specific load conditions, etc., get the maximum loads. The load effects are considered based on the elastic principles of mechanics. Then the resistance is computed using design strength capacitive structural elements. Then one can compute the allowable stresses in axial, bending, shear, torsion, etc. Then we say that the capacity should exceed the demand. Let us talk about the other method, which is load resistance factor design method, where the demand arises from the design loads. Now, in this method, the loads are obtained based on probability of exceedance of the method. Okay, I can give an example. What do we understand by probability of exceedance? We already saw that. Let us say you have an historical data of the past, historical data of wave height, that is wave amplitude, and wave period for the past 100 years. Okay, you have the data. So, wave height, wave period, you have the data. So, there are data available. What you do? You pick up the maximum value. Let us say the maximum available here, wave height was about, let us say 8.2 meters, and the corresponding period. You cannot pick up wave height one value and wave period one value. I mean, there should be a correspondence between these two. Okay? So, wave period corresponding is about 10 seconds. You picked up this. This method says you cannot apply this load directly. You must also find out what is the probability of exceedance of this load in the past. So, for example, if this combination has occurred only once in 100 years, then the probability of exceedance is practically close to 0. So, you should not pick up that kind of value where the probability of exceedance is very minimum, right. So, usually people look for a probability of exceedance of not more than 5%. Okay, 95% the load does not exceed, 5% can exceed. For example, in a given data of 100, 5 times this value can be exceeded. Suppose you have 100 data and you have chosen wave height of 5 meters and 6 seconds. In this 100 data, this combination exceeded about 4 times. Okay? So, you can take this value as the design load, a design wave, then the load computed from this way. Okay? So, this method estimates the loads based on probability of exceedance using the characteristic distribution of each type of load. Remember friends, the characteristic distribution of each load is not same. Okay? The dead load appearance or repetition or exceedance can be different from the earthquake load, different from wave load, etc. So, you can have a characteristic distribution, what assumes to be a load factor can be different for different kinds of loads. So, assume and compute this for different classification of loads, pick up that combination and obtain the design load. That is about the demand. Let us come to the capacity. Capacity actually is a resistance offered by the material through the member through the structural form. Okay? It is purely based upon the yield strength of the material only. Remember friends, in the previous design case, we said yield strength is not completely used, we have taken a fraction of that. If you carefully understand, I can write the equation here. The permissible value was actually yield value by factor of safety, right. We have reduced the yield value, okay, and took that as allowable stress in the material. But here you can use the full yield strength of the material. Okay. Of course, use some tolerances for manufacturing, etc. So, do not use 100%, it is generally 0.87, okay, 0.87. So, we have a small factor We do not say the allowable stress is exactly equal to sigma y or Fy, we say it is 0.87 of Fy. So, we take some factor, some fraction only to account for some tolerances in manufacturing defects, etc. So, you assume the design resistance factors based on the probabilistic approach, then compute the design resistance, which says strength by resistance factor. Okay. So, resistance factor can be, for example, 1.15. So, the design resistance is actually equal to strength by 1.15, which becomes 0.87, right, 0.87. So, I can say resistance is strength by 1.15, which is 0.87 Fy, which I wrote here. Okay. So, one can compute the resistance based on this approach, one can compute the demand based on this approach, and of course, the design philosophy remains similar, that the capacity or the resistance should exceed the demand for a safe design. So, LRFD uses different factors for load and resistance, and this method is purely probabilistic based, whereas allowable stress design method does not use any probabilistic based design at all, but uses only the characteristic value of the load of exceedance and then uses Fy with a factor of safety. There is no probability of exceedance considered in the load, it is taken as the maximum load in the historical data available to you and design the section. So, allowable stress design method does not use any probabilistic segment in estimating neither the demand nor the load, demand nor the resistance, whereas in LRFD it permits the probability of exceedance of any specific event to compute the demand as well as the loads. Okay, one may ask me a question, why this factor should be applied for the material? You know, material need to be homogeneous, isotropic, uniform thickness manufactured, and you should have the same quality control for the entire batch of production. But you will notice that for the entire batch of production, there is always a standard deviation in the quality of their characteristic strength. For example, if let us say 100 bars of diameter 60 mm is produced by a mill, usually you will notice that the yield strength and modulus of elasticity, which are the two pioneer properties of the material, which can be obtained by conducting simple tension test in the laboratory, do not satisfy all 100 samples. Okay. So, the acceptable limit is more than 95% of the samples should pass a value which should be equal to the sigma y and E taken for the design. For example, if you have taken sigma y or Fy as 350 Newton per mm square and you have taken E as 2.1 10 power 5 Newton per mm square as your design value, then if you test 100 samples, conduct simple tension test, compute Fy and E, the values what to tabulate from the results, 95% of them should exceed this. Okay? Then you can take this value as the strength of the material. So, only 5% of the sample can fall below this. So, that is the requirement of accepting this as a manufacturing sample. Now, friends, when we deliberately allow 5% concession on the quality control which can be used by the mill to produce a specimen, therefore, I cannot use this Fy as such. Okay. What if that rest 5% lot from the manufacturing sample has reached the site and you are using them for construction? To take care of that, we use a factor here. Okay. So, therefore, resistance can be computed based on this method, demand can be computed based on probability of exceedance method, can compare these two and then frame a design procedure, and that is called LRFD. So, let us slightly look more in detail about the design method. The load factors and the resistance factors, because LRFD stands for factors on load and resistance, both of them have different factors. Both these factors are selected for each type of load and strength parameters. For all loads, the load factor is not same. For example, for dead load, it varies from 0.9 to 1.3. For variable load, this factor can vary from 1.3 to 1.5. For environmental loads such as wave load, wind load, current load, etc., it can vary from 1.3 to 1.4. These are advised by the code. Okay. So, for all loads, the factor is not same, that is the point here. So, you compute the nominal loads and nominal resistance for each set of combination. The design loads and resistance are obtained then by multiplying the nominal load and the resisting load by a factor, and this factor can be different for different kinds of loads. For example, if I look at dead load, I will multiply 1.3. If I look at machinery load, 1.3. If you look at any sloshing effect of fluids, I will use 1.5. So, for example, for different kinds of loads, I will use different factors. So, I can easily compute the design load and design resistance by multiplying the nominal load and nominal resistance obtained from the parameters with a factor. So, now I have got design load, design resistance, then I will say capacity and demand, compare them, frame and design procedure. Okay. Now, let us try to apply this method to a tubular member for a design procedure. What are the different kind of stresses a tubular member can experience? One is an axial stress, which is simply load upon area, be it tensile, be it compressive, load upon area. Okay. Bending stress is m by I into y. It is very important, friends. Let us take a beam. Let us say this is my x axis, anti-clockwise x is taken as y and clockwise is taken as z axis. Okay. This is 90 again, this is 90 again. Let us say this member has a cross section of, let us say, B versus H, the cross section of this member. Okay. Now, if we take the cross section and draw separately, when you look this from this view, okay, I am drawing it here, this becomes my H and this becomes my B, and this axis, okay, now becomes ZZ axis, am I right? And this axis now becomes YY axis, am I right? Now, I can find IZZ, which is essentially BH cube by 12. I can also find IYY, which is essentially HB cube by 12. Can also find IXX, which is about this axis. Okay. I will leave it to you how to get IXX. It is a big question, but it is not similar to what we have here. Okay. Now, these are two cross sectional axes. When the beam is subjected to a loading, okay, the beam will start bending, right. Now, the moment applied is about this axis. So, the moment is mz. So, moment about z axis. Okay. So, if you say the bending stress is m by I into y in general, I must clearly say it is actually equal to mz by about which plane this is bending. Okay. Now, this is the plane or axis about which the beam is bending. So, I should use Ixx, and y will be the distance measured normal to this axis. So, I should say y. Suppose I am looking for the beam bending in this direction. The beam is bending laterally, which happens in lateral torsional buckling, right. In that case, the moment is about this axis. So, I can say sigma bending in this case is going to be my, then the bending is taking about this plane. Okay. So, I should say Iy, I should, for example, I am sorry, I must write here bending stress is mz by Iz into y. Okay. So, in this case my by Iy into z, because this is the distance now from this axis. So, this is z. So, friends, m and I are about the same axis, okay, and z is normal to that axis. The distance is normal to that axis. Okay. So, that is how the logic goes, we all understand that. I can compute the bending stress based upon this way, right. I can also compute the shear stress, compute the hoop stress, and we will discuss about all these things in detail as we proceed further with the design code examples and provisions of the code. Okay. Now, let us look at one by one. When the member is under axial tension, how do we compute? So, now I say the allowable tensile stress, which I can say as Ft, okay, is only 60% of Fy. This is as per the design code of practice AP-RP2A, class 3.2.11. So, we have this Ft as 0.6 Fy, okay, only 60% is allowed. Of course, Fy is the yield strength. Okay. Now, generally it gives you in megapascal. Megapascal is very easy. Mega is 10 power 6 and Pascal is Newton per meter square. If I multiply this to mm square, I get this as Newton per mm square. It means megapascal is same as Newton per mm square. Okay. Let us have this in our mind. No change, right. So, in axial tension, I can compute the allowable stress easily using this equation. The actual stress coming on is simply computed from the loads acting on the member. I can compare the allowable stress with the actual load or the actual stress, and if the allowable stress is higher than the actual stress, we can say the design is safe. Okay. That is about axial tension. But friends, when you move on to compression, then the problem is tricky, it is not same. Okay. For axial compression, first we must ensure whether the member will buckle. One may ask me a question, why I am interested in finding out whether the member will buckle? Because friends, if the member buckles, then the capacity is much lesser than the member which does not buckle. Okay. So, first I must ensure whether the member will buckle or not. One can ask me a question, why this is only applicable to members under axial compression. Take a member, tubular member, put some boundary condition, plain axial compression. You will notice, take a matchstick, keep it within your fingers, try to press it. Okay. You will notice that the matchstick will start bending. If we keep on pressing it further, it will keep on bending further. A stage will come where the matchstick will break. Okay. So, on the other hand, this phenomena of behavior depends on the cross section property of this matchstick. If you take a thick matchstick, you will not be able to break it at all. If you take a thin matchstick, you will be able to break it. So, on the other hand, it has got some relationship with this diameter to its length. In column design, we call this as slenderness ratio. Okay. So, APRP classify this slightly in a different way. It says first check whether the D by T ratio is greater than 60 or less than 60, where D is the external diameter, outer diameter, when T of course is the thickness. Okay, it is a ratio. Check this ratio first. So, friends, if the member chosen by you has got D by T more than 60, then it is not advisable to use a member. Now, let us take an example. A typical diameter of the column member in offshore structure system is, let us say, about 1000 mm. The thickness which we use is about 50 mm. So, let us compute D by T. 20. So, less than 60. Okay. If you take a member which is 300 mm and take a thickness of 5 mm, you will see the D by T is touching 60. So, this configuration is not good for offshore structures. Okay. So, one should first check the dimensions which are applicable for design. So, API says first check D by T before checking the slenderness limits. So, if D by T exceeds 60, then the procedure is different, but do not use it. If it is less than 60, okay, go with that. Suppose let us say I have a member whose D by T is less than 60. D by T is less than 60. Okay. Or let us say verse by verse equal to 60. In that case, I have to compute the allowable axial compressive stress. Is it not? I call this as FA, and FA is given by 1 minus KL by R square. Okay, let me write it the other way. 1 minus KL by R square by 2 cc square. Let me rub this. 2 cc square divided by 5 by 3 plus 3 KL by R divided by 8 cc minus KL by R cube by 8 cc cube times of Fy, where Fy is the yield strength of the member. Okay. I multiply this factor to an yield strength. That factor is given by this equation. Okay, this is square here. Please make a correction. This is square here. Okay. Now let us see what is this KL by R business. Now this is true only when KL by R is less than Cc. So let us see what is Cc and what is KL by R. Cc is the critical stress, which is given as 2 pi square E by Fy the whole root. Critical compressive stress, okay, 2 pi square E, whereas E is the modulus of elasticity, Fy is the yield strength of the material. So you know Cc. Then let us see what is KL by R. K is called effective length factor. Let us see what is this factor. This factor is given in table of section 3.3.1d of the code. I will give some examples. If you are using jacket legs, then the effective length factor is 1.0. If you are using deck truss web members, if you are looking for in plane action, then the factor is 0.8. If you are looking for X braces, then the factor is 0.9 and so on. So the table on this particular class gives you the effective length factor. Okay, so we can always choose what actually you want, where L is called the unbraced length, R is called radius of gyration. So if I have a cylindrical member and if I know this is my unbraced length, and if I know the outer diameter and the thickness, radius of gyration is actually root I over A, and we know I for a circular member, which is pi d power 4 by 64. Let us say pi d power 4 by 64, and area we know is pi d square by 4. Can always find R. If I know R, I can find KL by R because I know K. If I know KL by R, I can substitute the value here and no problem with the numerator. Okay, it's okay, fine. We also know what is Cc. Cc is given here. So now what I do, I will first compute KL by R, compute Cc. If this value is lesser than or this equation satisfied, we will use this. If it is not satisfied, if KL by R exceeds CC or equal to CC, then the allowable stress is given by a different equation. Let us say this is equal to now 12 pi square E by 23 KL by R square. Friends, you will notice that the numbers what you see here, okay, the numbers what you see in this equation, okay, these are all based upon empirical equations where extensive experiments and numerical analysis were conducted and the data were taken. Okay. So, these are all actually based upon experimental studies conducted by various researchers, and a debate has happened and this equation has arrived, right. So, now if KL by R exceeds CC, I have this equation to compute FA. If KL by R is lesser than CC, I will use this equation to compute, where K is the effective length factor, L by R is explained and CC is given. So, one can easily compute the allowable axial compressive stress for column buckling. Okay. Once we do this, then the condition is true only when d by t is less than 60. If d by t exceeds 60, what happens? If d by t exceeds 60, what happens? If d by t exceeds 60, the section will experience local buckling. When the section exceeds local buckling, then up to what limit I can allow this? So, d by t should be between 60 and maximum 300. Okay? So, in such cases, the critical stress CC okay, what we are using in this should be replaced. Okay? Let us see how we replace this in the next lecture. So, friends, in this lecture, let us look at the summary. We understood the design methods for tubular members. We said there are two design methods which are popular. One uses probabilistic tool or probabilistic methods, one is deterministic. And we have seen what are the different kinds of stresses which can experience by the member. And we also understood how to compute the permissible or allowable stresses in axial tension and axial compression. So, we move forward to understand further in bending etc. and shear in the next lecture. I hope you follow this and you understand clearly the design aspects which is being followed. By one example which we are using as AP-RP2A code, one can also use additional other codes like ABS, American Bureau of Shipping, to compute this. If time permits and details are available, we will test that also. Then we will make a design example and illustrate for the sake of viewers to understand how the design is actually done using this course of practice. So, follow the lectures and try to have more information from the textbook referred in SwayamPrabha website. Thank you. Namaste.